So this video is about putting the finishing touches on projectile motion. The chart that you see in front of you is the chart that I developed with the B cohort on Tuesday, mostly because their numbers are a little bit nicer because I gave them a uniform rounding tool to use so that our numbers came out a little bit more uniform across. So this is the chart of what was happening as I varied what theta was, what was happening to all the various quantities in this problem. We saw VIX get smaller and VIY get bigger. Let's just talk about why that is for a second, because VIX is found by doing VI cosine theta I, and this is VI times sine theta I. This is, of course, theta I. Notice here that the VIX is based on the cosine function. We know cosine is maximized at 0 and it's 0 at 90. So as we go from here to here, it makes sense that the values here go to 0 as well, since cosine of 90 is 0. Same thing here. This is based on the sine function. And so sine of 0 is 0, sine of 90 is 1. So as we go from 0 to 90, it should make sense that that gets bigger. Now, a couple of interesting things happens along the way. At 45, because we know cosine of 45 is equal to sine of 45, we're at 2 over 2. You get equal values there. And another couple of interesting things, 30 and 60 as complementary angles, meaning angles that add up to 90. We know that cosine of 30 is the same thing as sine of 60, and cosine of 60 is the same thing as sine of 30, right? So that the cosine of an angle is equal to the sine of its complement. And that's why you have this flip-flopping going on here, because of the symmetry of those functions, right? We had very clearly then the time increases as theta increases, which makes sense. The more you shoot something directly upwards, the longer it spends in the air. We'll skip this for a second. And the more I shoot something directly upwards, the higher up it goes. But we got this weird idea here, not idea, but weird function here, which is that x increased, then it decreased, and it reached a maximum of 45. So let's just talk about the factoid then. We said from a pattern perspective, as theta approaches 45, delta xt increases, meaning as you go from 0 to 45, it increases, and from 90 to 45, it increases. Meaning that you get a max range at 45 degrees. Now, that's not always true, folks. That's true in the context of this problem where we're on a flat plane. And so what this video is going to do is going to prove that. And we'll get to that in a couple minutes. The other thing, last pattern I want you to notice is, look at these numbers here. Now, they're off because of rounding internally within the problem, but you'll notice that the range for the 30 and the range for the 60 are approximately the same. They should be exactly the same. If we had the same rounding all throughout, or we didn't round throughout, we would find out that complementary angles give equal ranges. Those are the kind of last two factoids there that we needed about this projectile motion. And by the way, these facts are true only once again for delta y total is equal to 0. These facts are true, just true, right? That's why they're over here on this column. These facts are very specific to the context that delta y total is equal to 0 meters, and we'll show why in a minute. So I just want to draw a picture to illustrate what I'm talking about with this. So what we have here is the following. If I fire something at a low angle, right, it might go like that. Let's say it's a 15-degree angle. If I fire it at a 30-degree angle, it goes a little bit further, 30-degree angles. A 45-degree angle, right, it goes even further. And what happens here is that if I go up again to a 60-degree angle, right, it goes up higher, but it doesn't go further. And that's my 60-degree angle. Let's say a 75-degree angle, up higher, but not further, right? And so that's a nice picture that illustrates those patterns that we were talking about. You notice the 15 and the 75 have equal ranges. The 60 and the 30 have equal ranges. What's different there is the time lag between the two paths. Obviously, the higher path takes longer. Okay. So that's actually everything that you need to know for projectile motion, folks, right? So if you want to stop this video now, feel free. What I want to go on and do now is prove a lot of these things that we just saw by observation. So I'm being serious about this. If you're interested, please continue on with me. But if you're not interested, no big deal, right? Normally we spend 2 class periods on this in a normal year. We just don't have the 2 class periods this year, but I still want to give people the opportunity to see this. We'd be working our way through this. So there's 3 things that I want to prove to you in the rest of this video. One, that projectile motion has to be parabolic. 2, the second thing that I want to prove to you is that if the angle of launch, if I'm on a flat plane, that the maximum range is given at 45 degrees, and 3, that complementary angles give equal ranges. So here we go. The first one is actually really easy to prove. So let's say I have VI, and I've got theta I, boom, 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 boom. And I don't even care if it's a flat plane or not, whatever. We know, let's say up and to the right are positive. We know that if I had a little chart here, I'll do X and Y, okay? We're gonna have some sort of delta XT, some sort of delta YT. We won't assume it's 0 yet. VIX, VIY, okay? And this is gonna equal VI cosine theta, and this is gonna equal VI sine theta. I don't care about the final velocities. AX is going to be 0, and AY is going to be negative G, right? So we're just going to kind of roll on that premise for the moment, okay? Right, because maybe I'm not on Earth. Maybe G is some different value. It's not 9.8. I did say up is positive, so the acceleration is negative. If I were to look at these equations, then delta X total is equal to VIXT total plus 1/2 AXT squared, and then delta YT is equal to VIYT total plus 1/2 AYT squared. That's my premise. So the first thing I'm going to prove is that projectile motion is inherently parabolic. Okay, the way we do that is the following. So I'm going to plug in my accelerations here. So I have delta XT is equal to VIXT total. Coming over here, delta YT is equal to VIYT plus 1/2 negative GT squared. Now, what is the general equation of a parabola? Well, we know that y is equal to ax squared plus bx plus c. That's the general equation of a parabola. And what I want to do is kind of make this into the general equation of a parabola to show that the y motion is related to the x motion in this parabolic way. Notice here, I have these times. That's not what this is about. So I'm going to solve this for the time. So time total is equal to delta xt over VIX. I'm going to put that in here. So delta YT is equal to VIY, and I can get rid of this, delta XT over VIX. And this is minus G over 2 delta XT over VIX squared. And so then when we put this out there, I get delta Y total is equal to, and I'm just going to reorganize the terms there. I'm going to get the squared term first, negative G over 2 VIX squared times delta X squared plus VIY over VIX delta X. If I look at that equation, that says that at any given time, the y displacement is equal to whatever the x displacement is, right, times some constants. If you look at that, that's the same structure as this. I've got an x squared term, I've got an x term, right? Even better, notice the coefficient of the x term has a negative sign in this. What happens when a is negative when you're doing parabolas? That means the parabola opens downwards. And that's exactly what we have here. We have a downwards facing parabola. So there you go. This equation proves that any projectile motion forms a downwards facing parabola. And there you go. So that's the first thing I wanted to prove. Now, this equation is an atrocity. I mean, we don't want to use this. Let's keep doing what we've been doing for our problem solving. This is not an equation we want to use. It's too complicated, right? But certainly, it does fit our goal of trying to show that it fits within the parabolic format, right? There's also other neat things we can do about that, because, your turning point, negative b over 2a, if you were to do this, you would find out that that has consequences here, which are kind of interesting as well. But we're not going to go into that. If you'd like to, feel free to have some fun with that. The second thing I do want to prove is that supposition that if I'm on a flat plane, delta y total is equal to 0, that I know that you get 45 as the max range. So using that, here we go. I'm going to still do the following things. So delta xt is equal to question mark. We know delta yt is equal to 0. Vix is equal to vi cos theta, and viy is equal to vi sine theta. Ax is equal to 0. Ay is equal to, once again, negative g. We're going to do this more abstractly and not put in numbers. So the format of our solution is a little bit different. It's kind of the same as what before, except we now are going to assert that delta y total is equal to 0, making our expression a little bit easier. So this becomes vixt plus 1/2 axt squared. Delta yt is equal to viyt plus 1/2 ayt squared. And I should assert that these are t totals because I do care about the entire path. Okay, we know that that is going to go to 0, and we can plug in. So delta xt is equal to vi. In this case, I'm actually going to put in the vi cosine theta I t total. Here, 0 is equal to, we're going to go vi sine t theta I t total plus 1/2 negative g t total squared. All right, so now remember, what I'm trying to do is prove something for maximum range. So I don't want to actually take this and put that into there this time, because I'm actually trying to solve something for this. So being that that's 0, this equation now becomes factorable, right? Not always factorable, but because of that 0, I get a nice, not easy, but easier equation. I get vi sine theta I minus 1/2 g tt. There you go. Right? That means that tt is equal to 0, or I'll have to do some algebra here, or 0 is equal to vi sine theta I minus 1/2 g tt. Let's move that to the other side. 1/2 g tt equals vi sine theta I. Solving for tt, tt is equal to 2 vi sine theta I over g. Okay? Now, actually, that's a pretty interesting thing in and of itself because it verifies something that we saw before. Notice that tt, vi and g are not going to change in a given problem. Whatever the speed you launch at is the speed you launch at. But notice it says that, well, actually, this says that as sine of theta I increases, so does t. And we know that as theta increases, so does sine, because sine of 0 is 0, sine of 90 is 1. So that makes sense, the pattern we saw before, that as theta increases, so does the time. It actually does tell us that if we launched something faster, we spend more time in the air. But I think that's almost trivially, that just makes sense. You launch something faster, it spends more time in the air, and all the quantities get bigger as a result. So that's not too interesting, but there you go. But that's an interesting result in and of itself. So now what I'm going to do is I'm going to come back and bring that over here. So delta xt is equal to vi cosine theta I, and then we're multiplying that by this thing here, 2 vi sine theta I over g. Okay? So I've got the 2 vi's there, so that becomes 2 vi squared cosine theta I sine theta I over g. So what do I have there? Well, that's kind of looks gross because I've got the sine of theta I, cosine of theta I, Hopefully this is the moment when people say, hold on a second, that looks like something from math class, something I wasn't expecting, but there it is. Hopefully you're looking at the 2 cosine theta I, sine theta I, and you're like, that's familiar. It's familiar, or at least it should be, because that is one of the standard trig identities. You know those trig identities you use in math and you're like, no one would use them. Well, physicists use them all the time. It's actually super important to us. So that cosine theta I, sine theta I times 2, hopefully you'll recall, is equal to sine of the double angle. So that's equal to sine of 2 theta I over g. So that's a glorious result. So let's see what that tells us. Notice here, that says, well, as VI increases, so does delta xt. That just makes sense. But notice here that delta xt is now a function of sine of 2 theta I, not theta. So we know that theta is a maximum when theta is equal to, rather, excuse me, sine is equal to 1 when the argument inside of here is equal to 90. So in other words, sine of 2 theta is equal to 1 when 2 theta is equal to 90, therefore when theta is equal to 45 degrees. So therefore, delta x is maximized when theta is equal to 45 degrees. Boom, proof. QED, amazing. Now, once again, that's only true because of this, because this expression for time was only true in the context that we were able to factor this expression. It gets, trust me folks, a lot worse if this is not equal to 0. It's a problem I give to my ET class. They usually spend something like 4 to 6 hours on that problem. So we won't talk about it. So there you go, 45 degrees. Now, this also answers for us why complementary angles give equal ranges. So let's say theta is equal to, or theta I is equal to 20 degrees. Sine of 20 is equal to, put that in my calculator, 20 sine, boom, is equal to 0.34. Now its complement, actually we shouldn't even do sine of 20, excuse me, because I'm not plugging in 20, I'm plugging in sine of 2 theta. Oof, almost messed up my own analysis here. So that's sine of 2 times 20, or sine of 40, okay, and I get 0.643. If I do its complement, theta I, which is 70 degrees, right, because the two have to add up to 90, that'd be sine of 2 times 70, or sine of 140, and when we put that in, oh my God, you get the same result out. And that's that 2 theta, sine of 2 theta structure is the reason why that we get that. Because if we were to graph this, folks, right, sine of 2 theta, okay, so let's say I have 0, 45, and 90 here, and this is sine of 2 theta, go to 1, and then negative 1. What you end up with here is rather than having, normally if I do sine of theta, I get that as my answer, with that being 180 and this being 90, but because it's 2 theta, it just scrunches the sine curve down. And this is why also, if you think about it, that complementary angles give equal ranges, because now this figure is symmetrical about 45. So sine of 2 theta is symmetrical about 45, where sine of theta is symmetrical about the 90 there in that first bit. And so it's this symmetry that allows complementary angles to give equal ranges. Some people in class are saying, oh wow, that pattern looks parabolic. It's actually not parabolic. It is this first part of the sine function that is the symmetry. It is not a parabola, although it kind of looks like one. So there you go. So once again, you don't need to know any of that. If you know the fact that on a flat plane, 45 gives max range and complementary angles give equal ranges, and that this thing is like the projectile motion is parabolic, you've got everything that I want you to know, but I did want to spend some time in order to work through that for you in case you were interested.